Alrighty, we're good? Alrighty, so for the third talk in this session is a paper by Emmanuel Hainry and Romain Péchoux. Romain is giving the talk. It's called the General Non-Interference Policy for Polynomial Time.
Thank you.
Please. Yep.
So this work belongs to some family of work that belongs to the domain of implicit computational complexity. And our goal is to analyze the resource usage of program, but in a very general setting, which means that the resources can be time, space, energy, and so on. And the aim of this community is to provide machine-independent characterization. So by machine-independent, we mean that we want to consider programming languages and not low-level machinery. And then the characterization has to be implicit, which means that the programmer does not have to know in advance what are the bounds of the program that he wants to analyze. And if one managed to develop a method that is tractable, by tractable in this talk I mean, for example, decidable in polynomial time, then you've got some automatic static analyzer that can give a certificate to your program, ensuring, for example, that it runs in polynomial time. So this community has done a very intensive research for more than 30 years on distinct computational model. And let me now just rephrase what is the aim of this kind of research. So take your favorite programming language and take your favorite complexity class. So finding an ICC criterion, so an ICC characterization. So it consists in finding a subset of your programming language such that any program in the subset computes a function of the complexity class. This is called soundness. And conversely, completeness for any function of the complexity class, you want at least one program to belong to this subset. So this completeness is called extensional completeness because we are talking about functions. So talking about algorithm is a bit more difficult, and I will discuss this detail later. So if you think to the example of complexity class that we can analyze, we can take any standard complexity class, probabilistic complexity classes, quantum complexity classes, and so on, and so forth. And well, the programming languages have been studied in many distinct topics, such as lambda calculus, process calculi, probabilistic and quantum languages. And the kind of method we can use to analyze programs can be type systems, interpretation methods, or for example, it can be also amortized complexity, as in Kevin's talk just in the previous talk. So now, my talk is about non-interference. So people might ask, why is this talk related to non-interference as we are discussing complexity? And the point is that in non-interference, usually you take the memory, you have several levels of security that you want to guarantee, and you are going to say that the program is non-interfering in when the memory matches on the low level, you do the execution, and at the end you want still the execution to match. Okay. And now, at least 2011, there was a very nice idea by Marion. That was to see non-interference in a complexity analysis setting. So now you have two levels, 0 and 1. And 1 is a level of data that can have some computational power. And 0 is a level of data that have no computational power. And now you do the same. If you reduce the program at level 1 and the memory match at level 1, then you have to see that there is no flow from level 0, which means that the computational level is not impacted by the level that has no computational power. And you see that there is a slight distinction, is that we are in the converse order. So it's a kind of dual notion compared to the standard non-interference. But of course, this is not enough. And in order to get back to tractable functions, so to polynomial time, you need to add more restriction. And the restriction, so the complexity restriction we had, are that the space of data that corresponds to level 1 need to be polynomial in the size of the input, and the level 0 needs to increase at most by one constant. So now you can see level 1 data as the data on which you can iterate, and level 0, the data on which you cannot iterate. However, level 1 data cannot increase, whereas level 0 can increase, but only by a constant when you do some assignment. And then you have this theorem that is a sound and complete characterization of polynomial time, and that tells you that the class of functions computed by a program that follows this discipline and that strongly normalizes is exactly FP. So let me just illustrate this discipline by a very toy type system. So you see here I've got some kind of non-interfering type system, and you see that when some expression is increased by 1, I enforce the type to be 0. It corresponds to data that may increase. And in a while loop, the word is of level 1, which means that that's the data that drives the recursion. And so this is the kind of type system that we use into the safety. So the level 1 data, they can be assigned to level 0 data, but the converse cannot be done. And then type inference for such a system is tractable, can be done in polynomial time. So it depends on the number of levels you have. And if you allow strictly more than 2 levels, it's cubic in the size of the program. So let's look at an illustrating toy example. So we have one example that does let's say unary multiplication, and the second one is computing the exponential. So of course we want our system to pass on the first one, but to reject the second one. So assume we have already computed some addition function. So you see that the addition can iterate on its first operand and adds 1 at each iteration on its second operand. So the first operand drives the iteration, it types by level 1. The second one is increasing, it types by level 0, and it returns the second one, which means that you have an output of level 0. So this is an admissible type for add. And you see that when you try to type the multiplication, you can type it without any problem, just because everything goes well. But then when you try to type the exponential, it cannot be typed. So that's precisely what we want. And so the type system rejects the exponential behaviors and captures the polynomial ones. Okay, so now the purpose of this talk is to talk about what happens when we consider an object-oriented program. So here I'm going to take some representation where I represent my object memory by a digraph. And so it's not very, you cannot see this very well, but the red nodes correspond to everything that can be reached by some level 1 data. And the blue nodes will correspond to nodes that cannot be reached by level 1 data. So only by level 0. So on primitive data, we do some pass by value strategy, and there is no problem. So that's why the first characterization that I show works very well. But then when we consider reference data, when we assign the value of y to x, we may end up into the following problem, which means that we have some data of level 0 that points to some level 1 structure. And the problem is that this breaks, in some sense, the non-interference, because now you can alter the level 1 data, and this is not very good because it will break the polynomiality of the space and of the domain. So this problem has been kind of solved very partially in 2 ways. So the first suggestion was done by Levin and Marion at ICALP 2013, and basically they restrict the data structure to a digraph where the out degree is at most 1. So by doing this, they restrict again the domain to some polynomial size domain. which means that the result is covered again. And then a second solution was done by Emmanuel and I. And well, we have restricted the flows from level 1 to level 0 to only to data that are cloned. So when you clone the data in memory, then after the pointer is on some cloned data, and in some sense you recover and you solve the problem that was shown in previous example. However, let's consider this simple example of list reversal. So we take a linked list and we do some reversal. This example does not work on both solutions, just because the out degree of the graph considered is not 1. And here you see that we have some flow from level 1 to level 0. So y x is enforced to be of level 1 because it drives iteration. And y is enforced to be of level 0 because in some sense here we change the data, which means that it may increase. We cannot guarantee that it will decrease. Okay? So this example does not work for the two solutions that I have provided, and in the remaining part of the talk I will show how we can handle it. So now let's discuss a bit about intentionality. So it is a well-known result by Ajek that providing an intentionally complete characterization of polynomial time, that is a characterization that takes all the possible algorithm running in polynomial time, is a sigma 0-2 complete problem in the arithmetical hierarchy, which means that there is no expectation to have a tractable type system that has all polynomial time algorithms. So we define a notion of stratification, and in our setting we have a reduction from configuration to configuration. So a configuration is just a statement to be executed together with a digraph, so corresponding to the structure that I've just shown in the previous slides. And the reduction is indexed by a level, and the level n is the level of the innermost while loop word that drives this execution. Okay? And then we have a notion of stratification, and we are going to say that a program is stratified with respect to some non-interfering type system if for any configuration that is reachable from the initial configuration of the program P, we can check that whenever some configuration reduces at level n to some other configuration, the obtained configuration has to decrease or not to increase, sorry, at level greater than n, which means in some sense that if you restrict the subgraph of h prime to level greater than n, it has to be a subgraph of the subgraph of h at level greater than n. And we call STR for stratified the set of programs that follow this discipline. So I come back to my example. So here all the nodes are in red, and when I affect my so when I compute the first assignment, the two graphs, they do not change. Everything is reachable from level 1. So of course the graph of level 1 is included in the first one because it does not change. Then the same, and here in this example, so it's not visible here, but these two nodes here, they are in blue, which means that the red nodes of the second graph are strictly included in the red nodes of the first one. So by doing this reduction at level 1, we have some decrease into the reachable node at level 1. And then the reduction does not change, and so it means that this example follows this strategy, and so it is a stratified program. So now we have a result that says that the set of functions computed by stratified and strongly normalizing program is exactly the set of functions computable in polynomial time. And we also have a proper generalization, which means that the set of safe and strongly normalizing programs that I have just shown in the previous type system is strictly included in the set of stratified and strongly normalizing programs. So we capture much more algorithms than the first method. Let's say that now, if we want to rank this problem in the arithmetical hierarchy, we have shown that it is pi 0, 1 complete. So for this, we have used the result by Hainry and his co-author by showing that we can make a reduction of the blank tape non-halting problem. And if you remember Ajek's result about intentionality, so we have pros and cons. So first, of course, it means that our characterization is incomplete. We are losing some algorithm. But this was expected. Of course, the bad thing is that we are still undecidable. But the good thing is that we are one level below in the arithmetical hierarchy. So in some sense, we have a bit simplified the problem. And of course, compared to SAFE that is tractable, we are undecidable, but at least we have strictly more programs. So the remaining of this talk will be to see whether we can specify some decidable instance of stratification that allows to capture more program. Okay. So for this, so we have used some shape analysis techniques, and so in particular, we have based our work on an old paper by Mouli Sajiv and his co-authors that do some abstraction of linked list. And the graphs that I obtained, they can be abstracted this way. So we lose a bit of information, but the good thing is that by doing this shape analysis approach, we still have some information about the levels that can be accessed on the data in the graphs. And of course, one difficulty we have compared to standard shape analysis technique is that here we are talking about complexity, which means that we need to consider the program on all possible inputs. So it means that we need to put some restriction on our abstraction. So we have a notion of separability that assumes that the input that we have before the execution of the program, they do not point on the same location in memory. This is some hypothesis we make. And then we are able to use this abstraction. And we have designed some type system that use this shape analysis abstraction. So I will not go too much into the detail of the type system, but the point is that we just have some kind of side condition in the type discipline that just check at some point that the variable cannot be accessed by some level inside the program. And then we again have another soundness and completeness result, which means that stiff and strongly normalizing programs are included into shape analysis and strongly normalizing programs that are also strictly included in stratified and strongly normalizing program. And if we take Sajiv's approach, we can decide, we can do the type inference in time, in the worst case, exponential in the size of the program. So when we do our analysis, our program, so the difficult point is this assignment. We need in some sense to check that when we assign the tail of y, in some sense, y cannot be accessed anymore by level 1 data, so that it will not break the flow. And so the type system uses the shape analysis graph, perform this check, and we manage to type this reverse program. So the conclusion is that we have designed a new non-interference based techniques for capturing the functions computable in polynomial time. The good point is that we are a clear separation between the things about non-interference and the complexity requirement. It strictly generalizes the previous method. It's pi 0, 1 complete, and we can instantiate some particular instance that are decidable and that capture strictly more programs than previous methods. I conclude this talk here, and if you want to see more details about this non-interference based type approach, there are also characterization of many other complexity classes, including polynomial time, type 2 polynomial time, And of course, the model has been extended to many other programming language and paradigms, such as forks process, languages on graphs, and also a subset of Java programs with some implementation that is called complexity parser. Thank you.
Thanks very much. Oh, is my microphone on? There we go. There's a question, I don't know who's first, but there's a question back here, and then we'll get to you.
Hi, this is Anita from UMass Law. Can you quickly go to one of your early slides that showed the type system for safety? I thought I saw two statements which are like sequence, ST1, ST2, and the second one didn't have an expression. I'm just wondering.
Oh, so this is a typo, so this is a conditional.
Conditional,
If
okay.
E, blah, blah, blah. You just keep the levels unchanged.
Okay.
So of course, in this type system, you can add some subtyping rules. So I have just written here the main rules. I mean, so.
Okay, and what's intuition for the assignment?
What do you mean by inclusion?
The typing rule for the assignment. X equal to.
Oh, yes. So it means that if is of level 1, you can put the level 1 to level 0.
But
okay?
not the opposite.
But not the opposite.
Okay, great,
okay?
Thanks.
And of course, on values, no problem. But when you consider objects, then there can be side effects, and you can break the polynomiality of the system.
There's a question here.
Okay, so I am Xavier Rival from Paris. So I have actually a twofold question about the shape analysis that you have used. So you are using a TVLA-based shape analysis. So the first question I have is, have you considered also to look into separation logic-based shape analysis, which is another way to also compute a similar invariant? So I'm curious to know if you look into it and said it would not work for you.
Currently, we haven't, but of course that could be something of interest. Of course, what I find nice in this talk is that we have managed in our work to merge things about complexity, about non-interference security, and shape analysis. So you have 3 domains of research. However, of course, there are restrictions, which means that by doing the shape analysis, you just have information about the shape. So in some sense, if your algorithm is a bit too smart and is doing things very complicated inside, then of course you still are going to fail. But at least the good point is that we've got tractable instance that improves strictly the previous one. And then, of course, we are not expert on this. So if we find people from the shape analysis community that want to collaborate, we will be open to collaboration.
Sure. So, and the second part of the question, by the way, is also related to this. So you mentioned this assumption that you needed to have separation of, yes, the arguments of the function. So actually, this reminds me of things I've seen done in other analyses where if you did not have the assumption, it would really make it very hard. Was it the case for you?
No, it's not the case. But the important point is that this separability assumption is not preserved by the semantics. Okay, so this is clear. But then the point is that we need it because otherwise we end up into abstraction that are a nonsense with respect to the non-interference policy. However, if you think to the example reversal, even if you don't take such data at the beginning, then after, due to the program semantics, you end up into such kind of separable state.
Okay,
so this is you're welcome.
Okay, thanks.
Alrighty, are there other questions? Alrighty, then let's thank the speaker. Very nice talk.
Thank you.
That's the end of this session, and I think we have a coffee break. So.